15.2 Techniques for Computing Limits. Within this section, we're going to go over multiple ways that you can use in order to solve limits in order to come up with a specific answer. On slide 2, we're looking at a function at the top and it being described as a limit underneath. On the right-hand side, we have a graph describing this exact same limit/function and how it could be seen online. Now, when you are taking a look at a function such as this, you have to realize the fact that you have the ability to go ahead and simplify this function by breaking down the numerator into different factors. So here, what will occur is that we will be working with an x plus 1, x minus 1 on the top, and x minus 1 on the bottom. Now, due to that breakdown, you can now see that you can easily break this down into x plus 1 as your function. Now, within your limit, this can still occur the exact same way. You can simplify that denominator with a part of the numerator and be left with x plus 1. Now, the only issue with this is that you still have to go ahead and insert the 1 in for x. So 1 plus 1 will give you a final answer of 2 for this limit. Now, over here on the graph, you can see that from the left side, we are approaching 2. From the right side, we're also approaching 2. But even though we have an open circle at this location, does not mean that we cannot solve for the actual limit itself. Let's go ahead and take a look at slide 3. In slide 3, we are going ahead and we are plugging in our limit, our x value, into our equations. Now, it's extremely important to also pay attention to the denominator if you have a fraction. We're going to begin with our first problem, the top left, and what we're going to do is we're going to go ahead and plug in to our equation. Here, 1 squared plus 4 times 1 minus 5. That will leave you with 1 plus 4 minus 5, which will give you a final answer of 0. Now, getting a final answer of 0 is perfectly fine. The number one thing to remember is that you cannot have your denominator equal 0. Now, in this case for the top right sample problem, we can see that as plugging in the 1 into this equation, you would end up with 1 over 0, or basically undefined. Same thing would happen for this next problem. Absolute value of 0 is 0. 1 over 0 will give you undefined. Sine x over x. Once again, if we have x being 0, we are still dividing 0 by 0. Even at the case, we would still end up with undefined. As we go ahead onto our next problem, we do have the ability to go ahead and notice, because we do not end up with a 0 in our denominator, we can go ahead and plug in the 1 into our problem. Here we have 1 squared minus 4 over 1 minus 2, 1 minus 4 over a negative 1, and we end up with a negative 3 over negative 1, or 3 as a final answer. On our last sample problem, we have the square root of 4 minus 4, which would end up with the square root of 0, which will give you 0 as a final answer. So the most important thing to realize here is that if a denominator is 0, it will give you undefined. But if you have the ability to go ahead and solve that problem because the denominator does not equal 0, you would go ahead and plug in your x value into the problem. There are some general rules that you look at when you are evaluating the limits. Now, generally, when the domain is all real numbers, that is going to happen whenever you have a polynomial. So when the value of x you are approaching is not an endpoint of a domain, meaning the furthest left side or furthest right side, wherever it stops, at that point, you do not want for it to be the endpoint of that domain. So the value of the x you are approaching is not the domain restriction. And lastly, when the domain restriction can be removed algebraically. At this point, what ends up happening is the same scenario that we saw last slide, where we were able to simplify the numerator and denominator and able to remove out one of those expressions and be left with something else within the numerator. So slide 5. Now here, these are just generic rules that will help you have an easier time in you being able to answer and solve what these limits will equal. In this case, the limit of c is equal to c when x approaches a. Ultimately, what it's saying is that anytime that you have the limit of 6 when x approaches 2, it's already giving you the final answer of 6 because they're telling you that the limit will be 6 as x approaches that 2. And the same thing kind of happens at the bottom rule. The limit of x when x approaches a is a. What we're basically saying here is that the limit of x when x approaches 3 is 3. You're ultimately saying that at the end of solving this entire problem, what you would be doing is providing the same variable that is underneath the limit, which in turn gives you what you're approaching, which is your final answer. Slide 6. In slide 6, we go over two different types of functions, either polynomials or rational functions. Now, polynomials are just straight functions, going from the left side to the right side, while rational are fractions. Number one thing to keep in mind is that anytime that you do have a rational function, remember, your final answer cannot be 0 within that rational function. So as long as the denominator is not 0, you should be able to come up with a final answer. On our next slide, we take a look at various laws that limits have, which ultimately just break down what we are looking at into multiple different pieces of limits. So let's take a look at the first one. For sum, it says the limit of f of x plus g of x as x approaches a is. Now, when that is being given, ultimately what is happening is that they are going ahead and breaking apart this function of the f of x plus g of x into two separate limit problems. So they're going to grab this portion right here, and they're going to multiply it against the f of x, they're going to multiply it against the g of x, and that's how we end up with these two portions. Now, all we are doing is decompressing the actual original problem into two limits. Notice we are still doing the same operation that it says within it. Next one, the difference, same thing. We are breaking down the subtraction problem into two problems. Constant multiple. If you're multiplying a specific number against your function, it's just coming to the outside in front of your limit. For a product, you're multiplying the two limits against each other, and you can easily see that being done to the right-hand side. For the quotient, once again, you are doing the same thing. You are dividing the limit of f of x when x approaches a over the limit of g of x when x approaches a. Number one thing to remember is that the g of x cannot equal 0. The same thing will occur with some form of power. Notice that nth power is being pushed over to the entire f of x. And once that limit is multiplied against your f of x, notice you still have that nth power going to the entire limit. Same thing occurs with the fractional power. As we start to find our limits, we are going to go ahead and we are going to evaluate the limits. In order for us to evaluate the limit, we're going to go ahead and rewrite the problem itself. So here we have the limit of f of x is equal to 1/2 x minus 7. And that's going to be when x approaches 3. Now in this case, what's going to happen is that we are going to go ahead and plug in 3 in for x. So 1/2 times 3 minus 7, that is 3/2 minus 7. Now we can go ahead and switch 7 for a common denominator of 2, which would leave 3 over 2 minus 14 over 2, which gives us a final answer of negative 11 over 2. The same process will happen for b, where we go ahead and plug in our answer. Now here, the limit of g of x, where g of x is equal to 6, and x approaches 2. So our final answer here will be 6, or the limit of g of x as x approaches 2 would be equal to 6. Keep in mind, what ends up occurring here is the same rule that we were using before. And that is that any time that the g of x is being given to you, and they're telling you that it's going to be 6, that numerical value, whenever it's approaching 2, your final answer will be that 6, or that number, no matter what it is that is being given as far as the numerical side of it. Slide 9. Once again, we are being given the values for each one of our functions. Our f of x, g of x, and h of x. All we're going to do here is replace each one of these functions, so 4 minus 5, with their values over 8. Notice this will leave you with a negative 1 over 8 as a final answer. The same thing is going to occur with b. Notice here we have a constant that we're multiplying against for f of x and g of x. This will not change anything, so 6 times our f of x is 4 times g of x, which is 5, plus 8. So 4 times 5 is 20, times 6 is 120, plus 8 is 128 as a final answer. In C, we have g of x, which is equal to 5 to that third power. Our final answer here is 125. Now, in examples D and E, notice they do not provide the values for a function. They just go ahead and give you what x is approaching. In this case, you would go ahead and plug into these equations. So 2 times 1 to the third power minus 3 times 1 to the second power plus 4 times 1 minus 5. Here, 1 to the third power is 1 times 2 is 2. minus 3 plus 4 minus 5. In this case, 2 minus 3 is negative 1, plus 4 is a positive 3, minus 5 will leave you with negative 2. So once again, 2 minus 3 is a negative 1. Positive 4 and negative 5 is a negative 1. Negative 1 plus negative 1 will leave you with final answer of negative 2. In E, we replace the x value with 3. This would leave you with negative 5 times 3 over the square root of 4 times 3 minus 3. This would leave you with negative 15 over. Now, 4 times 3 is 12, minus 3 is 9. The square root of 9 is 3. Our final answer here will be a negative 5 as a final answer. In example 10, once again, based off of the equation being given, we're going to go ahead and replace our x values with 2's. So we're looking at 3 times 2 to the second power minus 4 to the second power over 5 times 2 to the third power minus 36. In this case, 2 to the second power is 4 times 3 is 12 minus 8 over 2 to the third power is 2, 4, 8. 8 times 5 is 40 minus 36. Here we end up with 4 over 4, which our final answer would be 1. We continue on to our next problem. Here we have the limit of the square root of 2x to the third plus 9 plus 3x minus 1 all over 4x plus 1. We're going to go ahead and replace the 2 in for our variables. In this case, 2 times 2 to the third power plus 9 over 3 times 2 minus 1 all over 4 times 2 plus 1. In this case, 2 to the third power is 8 times 2 is 16. 16 plus 9 is the square root of 25 plus 6 minus 1 over 7. Square root of 25 is 5 plus 6 is 11. 11 minus 1 is 10. So that would be 10 over, correction, not 7. That would give us 9. 4 times 2 is 8 plus 1, not minus 1. Plus 1 is 9, which would leave us with 10 over 9 as our final answer in this problem. Slide 11. In these problems, you're going to notice that we have the ability to simplify our numerator with our denominator. So in this case, our numerator breaks down into x minus 4, x minus 2 over x minus 2, x plus 2. In this case, our x minus 2's simplify out, and you can write it as x minus 4 over x plus 2. Once we have that simplified, we can go ahead and plug in our limit that we are approaching, which is 2. In this case, we're going to end up with 2 minus 4 over 2 plus 2. Negative 2 over 4 is the same as negative 1/2, which would be our final answer. Now, in B, we go ahead and break down our sample problem. Now here, we end up with the square root of x minus 1 over x minus 1. Now, in this case, although it may not seem as though it can break down, this actually can break down. This will remain as the square root of x minus 1 over square root of x minus 1, square root of x plus 1. At that point, we can simplify our numerator and denominator, and we're left with 1 over the square root of x plus 1. We go ahead, plug in 1. Square root of 1 is 1, which leaves us with 1 over 2 as a final answer. For example, C, notice in this problem over here, we have 3 over x minus 3 over 2, all divided by x minus 2. Now here, we want to go ahead and multiply by 2x across the top. This would go ahead and eliminate both of these fractions into a common term. So this would leave you as 6 minus 3x over 2x times x minus 2. Once we're at this place, we have the ability to go ahead and remove out something that we have in common, which is an x minus 2 keep in mind our numerator also has something that we can factor out, which is that negative 3. By us removing that 3, we have the ability to take out a 3, that would be a negative 3. That'll leave you with an x minus 2. Now, we do want to go ahead and flip this around, which might make it a little bit easier for you to be able to see. So this would come out as a negative 3x plus 6. We pull out a negative 3. We're left with x minus 2. So negative 3 x minus 2 over 2x x minus 2. In this case, our x minus 2's cancel out, and we're left with negative 3 over 2x. Once we have that solved, we go ahead and plug in our numbers. This would leave us with a final answer of negative 3 over 4. So on our last slide, slide 12, you can see that here we are going ahead and we are trying to simplify our denominator with our numerator. Our numerator would go ahead and simplify to be x plus 3, x minus 1 over the x minus 1. X minus 1 and x minus 1 cancel out, and we are left with x plus 3. We go ahead, we plug in 1 in for that value. 1 plus 3 is going to give us a final answer of 4 for our first problem. So we know that the limit of x plus 3 when x approaches 1 is equal to 4. We repeat the same process all over again. Here we break down our numerator to x plus 3, x minus 3 over x plus 3. This will leave you with just the x minus 3. We go ahead, we plug in a negative 3 minus 3. That would leave you with a total answer of negative 6. We rewrite the problem itself to be the limit of x minus 3 as x approaches negative 3 is equal to negative 6. In our last problem, here we are going ahead and multiplying by that common denominator. In this case, we are multiplying both the numerator and denominator by 3x. By doing that, we get rid of all of our fractions that are unwanted and keep them within the same denominator itself. So here we end up with 3 and 3, simplifying out. Notice x would come out in that denominator. X and x cancel out. We would be left with 3 in there. And we would have 3x times x minus 3. Now we're going to want to rewrite our denominator, which would give us a negative x plus 3. And in that case, when we do that, we actually factor a negative 1 out and be left with x minus 3 in the denominator as well. Once we do that, our x minus 3's cancel out. We're left with 3x over negative 1, or a negative 3x. We go ahead, plug in 3 in for that variable. And end up with a negative 9 as a solution. So when we rewrite this problem, it would be the limit of negative 3x when x approaches 3 would give us negative 9. This right here would be exactly how these problems would be rewritten, while also still finding the value that they would equal. If you have any problems or questions, please feel free to reach out at any point.